here's a context for adding graphs. The graph below shows two graphs, or two functions. Function A, or graph A there, is college enrollment in millions. So 2004, just over 6 million, and still, by 2008, still was just over 6 million. Graph B is university enrollment. And in 2004, it was just over 10 million, but it looks like it's going up. That by 2008, it was just over 11 million. And they're like, on the same grid, can you draw the graph of the total if you added these two together? Well, this graph plus this graph, and in the context, it makes sense. Like if there were 6 million in college and just over 10 million in university, does it make sense when I add those together that I would have got just over 16 million in 2004? In 2005, it would look like it's about the same for college, but like 10 and a half. So I'm going to say this looks like it's going to be 16 and a half in 2005. 2006 almost looks like we're going to hit 17 million. Very close. And in 2007, college enrollment went up. I think we are just over 17 million. And then for sure, in 2008, we're over 11 and over 6, so we're for sure going to be over 17 million. If I join these together, because the other one was joined together, there is our graph of adding two functions together. So when you have graph plus graph, describe your strategy here. What are we doing? We're just adding the y values, which kind of makes sense. If I wrote the functions in function notation, I called the red one f of x, the blue one g of x, and the green one h of x. And if h of x was supposed to equal f of x plus g of x, oh, the pretty colors I did there. Well, you've learned for a long time that f of x is just, like that's another way of writing y. Whenever we write function notation, is like that's another way of writing the y values. So if the new graph, h of x, which are its y values, are supposed to be the y values from the red graph plus the y values from the blue graph, it makes sense as a strategy that the x values stay the same and you just add your y values. And this is going to be a theme. Can you see that, if I change the plus sign to a minus sign and we subtract, what do you think the strategy is? Just subtract the y values. And multiplying will be just multiply the y values. And dividing would be just divide the y values. That's going to be the theme for graph math. Graph math. Okay, it's just the y values. Now some interesting things are going to happen along the way, which we're going to talk about. But here is our adding one. Next one, they have the stopping distance for a car is a function of the speed of the car, excuse me, when the brakes are applied, right? You're going faster, you step onto your brakes, and you would skid a little bit further than if you're going really slow and step on your brakes. Because cars don't, like, you could probably design a car, probably kill the person, that when you applied the brakes, you stop exactly where you are. Like, you just have, that brake button would have like, there'd be like some sort of titanium rods with very sharp points. You push that button, they get driven right into the ground, your car stops exactly right there, right? The dog walks nicely across the street in front of you, you never hit them, you go through the windshield still, right? That's probably why they have this skidding kind of thing, because otherwise you would die every time you stopped. So we have a braking distance, okay? That braking distance we're going to do in green. Your stopping distance doesn't just depend on how much you skid. Because the moment you see you want to stop, it's pretty quick, but the moment you see you want to stop, your brain goes, oh, I want to stop. It sends information to your foot has to move to hit the brake and push. And in that tiny amount of time, your car still moves forward. We call that, and it's on the graph here in blue, the reaction time distance. Does it make sense that how far you travel when you react, plus your skidding amount when you do react, those two together will equal your stopping distance. Now, right now, we've got this written this way. If I wanted to get the green part by itself, so I'm going to call the green one, since it's braking distance, are you okay with the green one? Oh, that's not green. Are you okay with the green one being green and being a B for braking distance?
Yes.
If I got that by itself, I would have to move the blue one over. So it would be the red stopping distance minus the blue reaction distance. If I just do that short. And now I've got a subtraction thing. So if I want to graph the green one on here, I have to take the red one minus the blue one. It's just rearranging our original question. And what's our strategy going to be? Just subtract the y value. So if we look on this graph, and we do a couple of them, I'm not going to do all the points, but here, if my stopping distance was 110, and at that 110, which is right there, my reaction distance is about 22 meters. If you're going 110 kilometers per hour, right? You see a squirrel run out in front of you, and you love squirrels. So you want to brake. By the time you react to braking, you've traveled 22 meters in front of you. If that squirrel is in the 22 meter range, ooh, it's sad squirrel day. Okay? But then you react and slam on your brakes, and we have to do 110 minus that 22, which would be about 88. So in green, I would go at about 88. You now skid for 88 meters. That's a long amount of skidding. So if that squirrel is in the 110 meter range in this situation, it's not good. And it's kind of a dumb squirrel because it would have to be like, look at you and be like, I don't know if squirrels flip off cars or what they do, and just like, and you slam on the brakes. And it does not move. Squirrels are pretty good at like deciding, hopefully, to move out of the way. The ones that are dumb are the ones that run out last second, and they're like, they don't have a time to think about moving out of the way. I wonder, I don't usually delve into squirrel thoughts, but it's happened, right, where the squirrel runs out, is right in the middle of your car, and you look back in the mirror, and they're like, still there. What does that feel like? Don't try this. Okay, I'm like, don't go run out in the middle of the street, lie down and say, I want to feel like a squirrel that didn't get killed. It's not worth it. But what do you think they're like, do they have, wouldn't that be somewhat, like, would they realize how close to death they came? I don't know. We should really interview squirrels. Okay. So, just subtract the y value. If we keep doing this, we could do, like, take another point, this one right here, and it's about 60 minus this one at that same time. Its y value is around 15. Our green point should be around 45. I'm going to do two more. This one here, 20 minus, looks like 8, should be around 12. Oops, that's not good. Oh, this one. This is my favorite one to describe in this situation. This one is 0. And the blue one's at 0. So, in this situation, you are sitting in a parked car. A squirrel runs out in front of your parked car. You react and travel zero distance while you're parked, while you react. Slam on your brakes, and you don't skid at all. And then your green point would also be zero. Kind of makes sense, right? But that would be describing that situation and what's happening. If we join these ones all the way through, that would be our braking distance function. We just took one function and subtracted the other. Okay. Next. And this is where the first one where we add some interesting things dealing with domain. And in this multiplication one, they took away context. Probably because they knew I would get way too distracted telling stories about squirrels, that this is, you know, get us back on track to finish this course, take away the context so Mr. JR doesn't go too crazy. I could make up his number. Okay. So we've got our blue function, which is g of x. I'm going to put a square around that. It's multiplied by the red function, f of x. And we want to see what we get when we multiply them together. What's the strategy? Just multiply. What? Okay, that makes sense. No problem. Now, interestingly, when you have two graphs, some things are easier to multiply than others. So I will pick some not good points to choose, and then I'll pick some, then we'll discuss what might be better points to choose. Here we go. I'm going to choose as a not good point, I'm going to choose when x is, I don't know, how bad do I want to make these points? They're mostly good points on here. I'm going to choose these 2 points because I'm kind of drawn to them. Right there where they cross. They're the same thing. Okay? This is going to be not good because what are my y values there? Oh. They're the same thing. Do they look like they're at about 1.7382? Maybe?
Yeah.
Yeah. And what's 1.7382 times 1.7382? No. No, it won't be. Try it. Try it on a calculator. See, mental math, this becomes a problem, right? That would not be a good point to choose because 1.7382 times 1.7382, I think it's pretty close to 3, actually, personally, but do you have it? Did you type it in?
Yeah.
What is it?
3.02133924.
That's pretty close. That's pretty. But mental math, not a good point. What, in multiplying, there are some things you are really, really good at multiplying by. 0. Great. If either one of them is 0, and you multiply them together, what are you going to get? 0. So, look. Hey, here they're both 0, so my green graph is going to be 0. At 2, the blue one is 0. So it doesn't even matter that the red one's not a nice number there. It looks like 1.48. Just saying. It's going to be 0 there. Good. It actually looks a little bit closer to 1.41. 0 is a really good one to do. Other multiplications that you're quite good at. 1. Yes, you guys are really good at multiplying by 1. What is, here the red graph, right? Here the red graph is 1. What is 1 times negative 1? Negative 1. You guys are good at this. Here, the blue graph is 1. And the red graph looks like it's 1.58. What's 1 times 1.58? 1.58. So I actually don't need to know the value. Just if the one graph is 1, the green graph will be right on the other graph. Does that make sense? Now, if you have other nice points on this graph, you could multiply them. But, I don't know. Like here my red graph is 2. And my blue graph looks like it's at 8. What's 2 times 8? It's not hard. But after you impress me with your multiplications of 0 and 1, I'm a little disappointed right now. 2 times 8, 16. So that would be like way up there. So our green graph looks, I'm going to guess, something like that going forward. What do we do over here? What do we do at -2? At -2, I have a point on my blue graph right here, at 8. But I have no point on my red graph. Can I multiply? So we find out that if one graph doesn't exist in a section, you can't multiply, add, or subtract. Both graphs have to exist in order for us to do something, right? So if something doesn't exist, you can't really put it into situations. What is your stopping distance when you're traveling -30 miles per hour? That doesn't exist. So we wouldn't have stopping. Okay. So multiplying, some key strategies. Maybe we want to write these down. Definitely a key strategy. To use your zeros and your ones. Either function 0, 1, super easy to use those points. You can use anything else that's nice. Like if both of them have nice points like that 2 and 8, then hopefully your times table is okay. Then you're going to be fine. But zeros and ones, key strategy. The hardest one is dividing. So here we're going to take the red graph divided by the blue graph. Okay, key strategy. What are nice things to do here? What are easy things to divide by or easy things for dividing? 0 for which? Numerator or denominator? Numerator. So, key strategy number 1. Oops, I don't want to use it. Numerator is 0. So let's go. My numerator is the red graph. Is my red graph ever 0? Yes. And 0 divided by anything is 0. So I'm going to have a green point there. Awesome. Okay. Other things that would be nice. Denominator is 1, yes. So my denominator is my blue graph. My blue graph is equal to 1 here and here. Okay? They're technically not nice values, because my red graph there looks like it's 2.8, maybe? But if you took 2.8 and divided it by 1, you would get 2.8 again. So we can go, where the blue graph is 1, we can go straight up, and it's going to be exactly on the red graph at that point. Does that make sense? Okay. Other nice points. And at any time, if there is a point that is actually you can do, like I would look on here, and like if this red point's at 1, this blue point is at 8. If I did red divided by blue, I would get 1 divided by 8, which is 1/8. At least the numbers I can think about, I could label 1/8. Same thing over here, it would be the same on this side, right? 1 and 8. That would be 1/8. What is the most problematic point in this example? What would cause us, like, issues?
0, 1.
Yeah, if the denominator is 0, that's going to be bad. Because then, see, I can't even spell it now. Yeah, I'm okay. Already causing issues, even in my spelling. Denominator is 0. That's bad, right? Are we allowed to divide by 0? No. Think back to chapter 2, into our rational functions unit. What were the possibilities when you had a non-permissible value? Non-permissible values ended up being one of two things. Do you remember the two possibilities when you had a non-permissible value? Vertical asymptote or hole. Okay? If, it's very rare that they do a whole example. I think there's one in the homework. These are the bad points right here. Here and here. When do we have a whole? Is when factors cancel out, right? So that technically, if your red graph and your blue graph intersected at that place, most likely it would be a hole in your graph. But if only the blue graph, in this case, only the blue graph is there, and this will happen most of the time in these questions, then that non-permissible value will become a vertical asymptote. So dividing is definitely the hardest one in graph math. Graph divided by graph is the hardest one, because you could have asymptotes or holes. Most of the time, they're going to be asymptotes. I think there's an, see if I have, yeah, if you look at your homework on page 269, that one's going to have a hole in the dividing, because they intersect on the x-axis. So when you get to the homework on page 269, one of them's going to have a hole. Okay. There we go. We got asymptotes. So now, when you have asymptotes, then your graph goes towards the asymptotes. Does it not look like the green parts, the dots that we've drawn, seem to go like this? And it does. The other key point right? What happens when you do the same divided by the same? What do you always get? 1. If they're the same, this is where they where the two graphs intersect, they're going to be the same y values, right? I mean, it's the same strategy, just divide the y values. So that, on my graph, they're the same right here. This, oh, I guess my graph should have been, my green graph should have been 1 right there. Let's make it a little wider. Same thing here, they're the same. It's going to equal 1 where they're the same. Other hints you can do is the following. If you had a positive number divided by a positive number, that's going to equal a positive number, right? If you have a positive number divided by a negative number, what are you going to get? A negative number. And if you had a negative number divided by a positive number, what are you going to get? Still a negative number. So I'm doing red divided by blue. Can you see in this, if I split up my graph into three sections, section 1, section 2, section 3, if I look in section 1, can you see that the blue graph is negative and the red graph is positive? And if you would divide negative over positive, what would you get? You would get a negative. So if you picked a number, here the red one is 4. I don't know what I'm even dividing by. I mean, it's hard to say, but it should be negative. So I know that this section here is going to be negative. I'm also going to use some strategies to tell you this. It's going to look like this, here and also over here. In fact, I'm pretty certain there's also an asymptote here on this graph. So we're also going to use a lot of our skills. When we get to the dividing part, we're going to use a lot of our skills from chapter 2. The blue graph is, what would you call that shape? Some sort of parabola? And it's going down. I don't know if it's a 1 in front. It might be negative 2x squared. Yeah, it's a 1. It goes over 1 down 1. So I know it's a negative parabola. Okay? What is this shape? It's absolute value, but if you only took half of it, it's a line, right? What are lines like? Y equals mx plus b of some sort. From chapter 2, whenever it's bigger on the bottom, there's an asymptote at y equals 0. Remember that? That's how I knew this asymptote was there. That is not easy to see with just graph divide by graph. So another strategy that we're going to use in this unit is if you know what they are, and this is not always the case, sometimes you're screwed. You're like, I have no idea what that graph is. But if I have a parabola divided by a line, I'd be like, oh, I know there's going to be an asymptote at y equals 0. And you'll get things like that. Okay? So the dividing ones are going to be the most complicated as far as stuff goes. So from 4.1, you can circle question 1 and question 2 and question 3. That can be your questions for homework. And we'll just, again, you notice this was a math lab. We did it together. Often we did math labs. Sometimes we skipped them. Sometimes we did it together. The purpose of a math lab is to give you an experience with something before they formally teach it in the next part. So 4.2, which we're going to start right now, is formally teaching what we just sort of were playing around with in 4.1. So we're going to do a little bit of the notes getting started in 4.2. I know you could plug numbers in and figure each of those out, so we're going to skip that, and we're going to skip the construct the understanding, and just go to the notes on page 273. I want you to highlight some stuff, and I also want you to get introduced to some notation. Because in this unit, they have two forms of the notation. One that I call nice notation, and one that I call not nice notation. And the exam always likes to be like, the nice notation is so intuitive and easy to understand that of course they never ask it on the exam because it's too easy. If you add two things together, f of x plus g of x makes total sense. And if I took this question here and I said, what is, from the red graph, what's f of 2? And then I got you to add, from the blue graph, g of 2, you would have no problem solving this question. You'd be like, oh, I know that f of 2 is 2. And that g of 2 is minus 1. So if I did just adding my y values, 2 plus minus 1, I would get as a final answer in green 1. And sure enough, if we graph these things together, that's where that point is. So What do they do on the exam? They introduce you to the not nice notation. And it will screw you up. So they, instead of asking f of 2 plus g of 2 like this, where you'd be like, that totally makes sense, I understand what's going on, they're going to write it like this, bracket, f plus g, bracket 2. That looks confusing. It is. In fact, whenever you get the not nice notation, the first thing I would do is change it to the nice notation. This just means f of 2 plus g of 2. But you should see, oh, people add things together, then multiply by, people create all sorts of bad math with the not nice notation. But there's going to be not nice notation for each of them. And every time you get the not nice notation, please change it to nice notation. And again, notice here, the green graph only exists where both the red and the blue graph. So they talk about domains only exist. So that's adding functions. We're going to do the same thing on the not nice notation for subtracting. There's nice notation. There's the not nice notation. So they could ask you, what is f minus g of 2? Then I would like you to first change it to f of 2 minus g of 2, and your life will be easy. Because I know you can plug in numbers into f and plug into g and figure it out. Right? Function notation. What this means is, when the x value is 2, what's the y value? In g of 2, it says, when the x value is 2 on your blue graph, what's the y value? And multiplying. Oh, multiplying. I've seen all sorts of not nice notation. Here's the nice notation. Here's one form of the not nice notation. I have seen, here's another form of not nice notation. They just put them squished together, right? Because when you have things squished together, it means multiply. Or I've seen, like, with the old school x is multiplication. Oh my goodness. There's so many ways you can screw yourself up with not nice notation with multiplication. Dividing too. You know, like f over top of g like fraction, f slash g like a dividing sideways, f with a dividing sign, then f g with a minus 1. Oh my goodness, like we could really mess you up. And then the problem with the g to the minus 1, then you might think it's the inverse function instead of the wrong. Oh. Not good. And again, what did we notice for multiplying? We would probably, like, for key points, notice they definitely use these ones where something is 0. When the red graph is 1, they use that point. When the blue graph was 1, they use that point. So that is multiplying. And if we want to do the dividing, we have to turn to page 275. And we can highlight the nice notation and the not nice notation. And of course, they could have a whole bunch of not nice notations. And anytime you have this, I would just change this to the nice notation. All right, that's where we'll end for the day.